Welcome back to CS270. In this video, I'm going to talk a little bit about exceptional control flow and about some of the low-level support for exceptional control flow on the processor, that is to say, exceptions. In a later video, I'll talk about processes, controlling processes, and then in more detail about signals. Um, so far, we've had programs running, and we've only really considered what happened within the program. So the program was executing one instruction, and then another instruction, and then another, and so on. So that's the control flow of that process. And, well, in the CPU, the same thing happens. The processor runs one instruction, and then another instruction, and then another, and so on. But then how do we handle multiple processes on a system, for example? Or how do we have the processor respond to events that are happening? That's why we need exceptional control flow. So far, the only ways we've had of doing control flow or of changing the control flow and not just executing one instruction after another, after another, after another, were to have jumps and branches. So that we would transfer control to a different instruction, perhaps conditionally based on the results of a previous instruction, and then the related call and return instructions to transfer control to a subroutine, pushing a return address onto the stack, and then to pop that address off the stack and go back to the caller of the subroutine. So all of these are reacting to changes in the program state. The program executes a jump instruction. The program executes a conditional branch instruction. The program executes a call instruction, a return instruction, and so on. The return address that the return instruction goes to is stored within the process, in the process's memory on the stack. But for a complete operating system, we need more than that. We need to be able to react to things that are happening on the system. Whether that's hardware that's signaling that something just happened, or an instruction doing something that it shouldn't be doing, or the tick of a clock. We need to be able to handle those, and we do that with exceptional control flow. So exceptional control flow exists at different levels of a computer system. Today we're going to talk about the low-level mechanisms implemented by the hardware. Now I say implemented by the hardware, but really it's a partnership between the hardware and the operating system. The hardware detects that some event happened. Then the hardware alerts the operating system, transfers control to the operating system, and then the operating system decides what to do about that particular event. In some cases, those events might be intentional. In other cases, they might be accidental. We'll see some of the details about that in this video. There are higher level mechanisms too that we'll talk about later. Context switches, so going back and forth from one process to another, or from a process to the kernel, to the operating system. Signals. So these are a way for processes to indicate to other processes, or for the kernel to indicate to another process that something's happened. We'll see more about that in lecture 14. And non-local jumps I'm not going to talk about very much. You can read more about those in the textbook, or you can look up the set jump and long jump functions. These are basically a form of exception handling, kind of like throw and catch, but a lot more low level in some ways, implemented by the C library. So we'll look at context switch and signals in later videos, but for now I wanted to focus on exceptions. So there are several different kinds of exceptions we'll get to, but fundamentally they're all about transferring control from whatever process happens to be running to the kernel of the operating system in response to some event. That event might be external to the processor. It might be something that's happening within the processor. It might, in fact, even be an instruction that explicitly asked for this to happen. We'll see why we might want to do that in a minute. So I've said kernel a few times. The kernel is the core of the operating system, the part that's always present in memory, always loaded, waiting to handle requests from the user or handle things that happen in the hardware. Um, the operating system is more than that. You might consider a program like Bash, the shell that you're typing commands into when you log into a computer. You might consider that part of the operating system, and that's not an unreasonable way to think about it, but it's separate from the kernel. The kernel, in particular, runs with higher privileges than what's called user code. So a program running on the computer has access to its own memory. That's it. It doesn't have access to the hardware. It doesn't have access to the memory of other processes. The kernel does. Kernel code is typically running with higher privileges, has access to the memory of all processes, or whichever ones are currently loaded into memory, and is able to interact directly with the hardware. So when an event happens, and there are several kinds of events, we'll see some examples of those later, the user code is running. At some point while it's executing this instruction, iCurrent, an event happens. The hardware transfers control to the kernel. The kernel takes a look at what event happened, what exception it was that caused it to get control, does something to handle that. What it does will depend on the particular kind of exception, and then does one of three things. It will either return to the current instruction, the one that was interrupted, to repeat it. That might be necessary if we've changed things so that that instruction won't trigger an exception the next time we've run it. Page faults, for example. It might transfer control to the next instruction because iCurrent here was able to finish. We'll see some cases where that happens. Or it may simply abort the entire program. The exception might be something like the user pressed Control-C. Or it might be something like we tried to access memory that we don't have permissions for. So within the hardware, there is an exception table. This is also sometimes known as an interrupt vector, especially on older systems. When I was doing DOS programming in the 90s, interrupt vector was the term that was used for this. And the exception table is just a big table of addresses of code. So when an exception comes in, the hardware, the CPU, will go to one particular slot in this exception table, depending on what kind of error it was. Maybe it was a protection fault, or maybe it was a page fault, or maybe it was a divide by zero. Each of those will have a separate entry in the table. It goes to that entry that has the address of some code, and it jumps to that code. That's code running within the kernel. So how do exceptions get triggered in the first place? Well, there are two different kinds or four different kinds, depending on how you look at it. Talking about two different kinds, they're asynchronous and synchronous exceptions. Synchronous exceptions, we'll see in a minute, will divide up into three other kinds, but asynchronous exceptions are things that happen external to the processor. They're also known as interrupts. So most processors, x86, 64 included, have a pin or a series of pins where if something sends a signal on that pin, maybe if the pin's voltage is raised too high, 1.75 volts or 3.3 volts or whatever that is, depending on our processor, the CPU will detect that and jump to a particular one of those exception handlers. Typically, the operating system handler for that will do whatever it needs to do to handle the notification we got from the hardware, and then goes back to the program, to the next instruction. There might be a few exceptions. Actually, one of those exceptions is the timer interrupt. So the timer interrupt, well, there is a clock chip attached to the CPU or somewhere on the motherboard that will every so often, maybe every 10 milliseconds, it can usually be configured, send a signal to the processor, trigger an interrupt by asserting that interrupt pin. Uh, when that happens, the kernel takes over, takes control, and with the timer interrupt in particular, this is how the kernel does task switching, switching between different processes. So that even if we have only one core on our computer, we're only able to run one instruction at a time. We can still run multiple programs at the same time by switching back and forth between them frequently. Um, Other kinds of interrupts might be things indicating that some external device has data ready for the processor. For example, maybe a network packet came in. The processor needs to alert the operating system so the operating system can do whatever it needs to do with that packet. Run it through the firewall maybe, and then if it's destined for some program on the system, send it to that program. The same thing if we make a request to read from the disk. Reading from the disk takes a really long time. We don't want the entire computer to be frozen just waiting for that to finish. So when a program tries to do a read or ask the operating system to read from the disk, it will be suspended, other processes allowed to run. And when that data comes in from the disk, we get an interrupt on the processor. The operating system is notified, and the operating system can then load the data into the appropriate place in memory and go back to the program that was waiting for that data to come in. And there are other things as well, like pressing Control-C at the keyboard, or really pressing any key at the keyboard. The difference is with Control-C, we usually handle that in a different way from most keys. So those are asynchronous exceptions, but there are also synchronous exceptions. So asynchronous happen as a result of something outside the processor. Synchronous exceptions happen as a result of running a particular instruction, and there are three subtypes. Traps are intentional synchronous exceptions. We executed an instruction, and the point of that instruction was to transfer control to the operating system. System calls are one big reason we would do this, and really the major reason we would do this. If we want to have the operating system do something on our behalf, remembering that user programs aren't allowed to access the hardware directly, they have to go through the operating system, then we need some way to get the operating system to run, and we do that with a particular trap instruction called syscall. We'll see an example in a minute. Also, breakpoints are often implemented in this way. If we want to set a breakpoint at a particular address in a program, our debugger will, at that particular location within the program's code, replace one of the bytes with a byte that stands for a breakpoint instruction. When that breakpoint trap instruction happens, transfer or control is transferred to the operating system. The operating system hands control back to the debugger, and the debugger can do whatever it needs to do. Maybe wait for user commands or so on while the program that was running is paused. And there are a few other special instructions other than syscall and breakpoint that do the same general thing, though they're not as commonly used on something like a Linux system, for example. So when a trap executes, once that trap is finished, we want to return control to the next instruction. We don't want to run the trap again and again and again. We don't want to return back to the very same trap instruction. So we'll go on to the next one. So those are traps. Those are intentional exceptions caused by instructions whose point is to raise an exception. There are also faults, which are unintentional but possibly recoverable. So the big example there is a page fault. If I try to access memory and that page is marked as invalid, that doesn't necessarily mean my program has an error. It might simply mean that virtual memory hasn't been loaded into physical memory yet. If that happens, the operating system will need to take over, load it, and then come back to our program and restart that instruction. Protection fault is another example. There, for example, I try to write to a region of memory that is marked as read-only. There, it's more likely that I won't be able to recover. The operating system isn't going to say, for example, you wrote into some read-only memory, I'd better mark that memory read-write for you. That would defeat the entire purpose of having those memory protections. But sometimes things can happen there in particular situations. Floating point exceptions might be another one. If we set up the floating point unit in our processor um, in such a way, we can ask it to raise an exception whenever there's an overflow or an underflow or so on. So when we get a fault, the operating, as with all exceptions, we transfer control to the operating system. The operating system then decides, is it able to fix this problem? In the case of a page fault, it may well be. If so, once it finishes handling it, it re-executes the instruction that caused the fault, and that instruction runs again and hopefully doesn't cause a fault this time because we fixed whatever it was that caused that to happen. Sometimes, for example, a protection fault, we would instead want to abort the process. And even with a page fault, there might be situations where we want to abort the process. That's what a segmentation violation or SIG-SEGV is all about. The third and final kind of synchronous exception is an abort. This is something that was unintentional and there's no way we could possibly recover from it. For example, if I try to execute an illegal instruction, that most likely means that in my process I've transferred control, I've jumped to some region of memory that isn't actually supposed to be machine code at all. The bytes that are there, or the bytes at that particular address, don't form a correct instruction. If that happens, there's not much point in trying to keep going. Chances are the next instruction would be either invalid or at least junk that I don't actually want to run, and so on. Other kinds of aborts might be if we try to access memory and the memory hardware tells us, hey, there's a problem. This particular word of memory has been corrupted. That's something called a parity error, which you can read up about on your own if you're interested in how that's implemented. But if that happens, again, there's not much we can do about it. If memory is corrupted, we really don't want to keep trying to run the program that encountered the corrupted memory because it's probably going to end up doing the wrong thing. It's much better to detect the error, stop the program, abort it, rather than have it keep limping along and hope that eventually the problem fixes itself. That could lead to us doing a lot of things that we didn't intend to do. So when we have an abort, as the name suggests, the operating system aborts the process that caused it. There's not much point in keeping it running in those situations. So let's take a look at a few examples. So first of all, system calls. So these were one of the kinds of traps which were a kind of synchronous exception. So the system calls are the services that the kernel provides to processes, things that it can do on the process's behalf. Things like opening and closing a file, reading from and writing to a file. Well, why can't a process do those itself? Well, besides the issue of complexity, if the process had to deal with the disk hardware directly, our programs would be a lot more complicated. There's also the issue of safety. I don't want a program to be able to read from just anywhere on disk, only from particular files that it has permissions to read. So the operating system needs to handle these, or the kernel in particular needs to handle these. Each system call has a number. The set of system calls is, and this is just a small subset listed here, the set of system calls differs from one operating system to another, although there are some commonalities. All the ones listed here are going to be present on every Unix system, whether that's Linux or Mac OS or something even more old school. The particular numbers associated with them aren't necessarily the same, and each operating system will have its own set of additional system calls for features that are specific to that operating system. So, as an example, your process might call open. Notice this is the open system call, not the fopen library function in stdio, and also not the iostream open in C++. This is the very lowest level way to open a file, which you could read more about if you look back into last week's slides. So we call open, we call it like a function because really it is a function. Within the standard library, there's a function called this, which is a wrapper around an even simpler function called underscore underscore open, whose purpose is to invoke that system call. So there is an instruction called syscall, the entire purpose of which is to raise an exception, transfer control to the kernel. Calling or raising a syscall exception is kind of like calling a function in some ways, in that we need to be able to pass arguments to the kernel to tell it, for one thing, which system call we want to do, but also what the parameters of that system call are, what the file name I want to open is, what flags I want to use when opening the file. So this underscore underscore open function, which is within the C library, does several things, but the important ones are it loads the numeric code for the open system call into the RAX register. Here we're using EAX, but that's because we have something that fits in 32 bits. Then it executes the syscall instruction. This transfers control to the kernel. The kernel does whatever it needs to do to open the file, checking whether the process is allowed to open the file, setting up the data structures within the kernel and within the process, and then finally returning a file descriptor number and coming back to the next instruction after the syscall, where we check the return value of the syscall to see if there's an error, and we'll do some other things based on that. Finally, the underscore underscore open function returns, comes back to the open function, that returns, and we're back to our code that called open. So notice that the arguments to system calls, while they are passed in registers in a similar way to function arguments, don't use the same set of registers on Linux. That is, the first argument goes in RDI, the second in RSI. That's the same as functions, but then the third argument is RDX instead of RCX. The fourth is R10, and only then do we have R8 and R9. Most of the time, this isn't actually important to someone programming on Linux because typically you don't invoke the system calls directly, but rather you use these wrapper functions. Also, system calls in that return value, they might be returning a number indicating success. For example, open will return the file descriptor number, but if they return a negative number, that indicates there was an error. And the particular negative number that the syscall returns indicates what the error was. So you saw error no back in the Lab 2 video, or if you were reading Lab 2. Error no is a global variable set up by the C standard library that holds a numeric code indicating what the last error to happen was. Well, the system calls themselves don't set error no. Instead, they return one of those error no constants. For example, ebadf. Now, those constants are usually positive, so to make sure we indicate it's an error, the system call returns the negative of that. Then, one of the jobs of a function like underscore underscore open, or possibly the open wrapper, is to take that numeric code that we got from the syscall. If it was positive, just return it back to our caller. If it was negative, then instead return -1 to the caller, but also set the error no global variable to the positive version of that error code that we got. All right, so that's a system call. which was an example of a trap, let's take a look at a fault. So here I have a program with an array, and I write into that array. So doesn't seem like there should be any problems, but remember, when we execute a program, we don't load all of that program into memory all at once. Instead, we use demand paging, meaning we just mark those pages as invalid, and when we try to access them, the operating system will load them for us. In this case, we have a global variable that is uninitialized, which means it will be filled with zeros, but that also means within the executable file, it's stored in the BSS segment, meaning the array isn't actually stored in the executable file. So when the program runs, or when we first access the memory inside this array, the operating system will need to map a page for us. Set aside a page of virtual memory, of physical memory, point the virtual memory page that we're referring to here to that physical memory, and then come back to our program. So we execute the move instruction, causes a page fault. The operating system would either copy the page from disk if it is something that's backed by disk, or set up that anonymous page of zeros, return back, and re-execute that move instruction. Because when it caused the fault, it wasn't able to do what it needs to do. It wasn't able to store that number into this virtual memory address because that virtual memory address wasn't mapped. Now that the operating system has mapped it, we're ready to actually do the movl instruction. So we come back to the movl, do that, and then the program keeps going. So that's one way we might have a page fault, but that page fault could also be an invalid memory reference. So here I'm referring to the 5,000th element of this 1,000 element array, and there's a pretty good chance that that page of virtual memory is not just marked as invalid, but it's not mapped to anything at all. So as with the previous example, when our program executes the instruction, that raises a page fault exception, transferring control to the kernel, and now the kernel will look and see that there isn't anything to load from disk. This isn't supposed to be an anonymous page of zeros. It's not supposed to be mapped at all. So because of that, the operating system will signal the process, which means not going back to the move instruction, sending it a signal which typically will result in the program terminating. So this is sig-segv, which is associated with the dreaded segmentation fault message. We'll see in a later video more about signals and how they work. It turns out the process can do something about this. Of course, it can't make the instruction access memory. It's not allowed to access, but it could do something other than simply terminating. All right, so that's all I wanted to talk about for now. In the next few videos, we'll see about processes, about how task switching works, about how we create new processes, have processes execute things, and wait for processes to finish. So we'll see more about that later. Thanks.